In this lesson, we will also discuss the ratio and root tests. In addition to this, we will prove whether various types of series converge or diverge using all of the tests we have learned thus far. So just be aware that when you're working on your homework and your quiz, there may be a series where you have to apply the alternating series test or use the comparison test, or some other test that wasn't explicitly given in this particular section. It also is the case that your textbook has a list of all the tests and when they apply that you can reference. So first of all, here is what the ratio test says. So we have that a series converges absolutely if the limit of the absolute value of the n plus first and nth terms is less than 1, and diverges if that ratio is greater than 1. And the ratio test is inconclusive if you have that limit is equal to 1. Test is awfully similar. So let's determine whether this series is absolutely convergent, conditionally convergent, or divergent. So remember that the ratio test and root test both test for absolute convergence, and absolute convergence implies convergence. So the ratio test works best with factorials and powers. So for this one, I'm going to apply the ratio test. So make sure you tell me which test you are using. A sub n will be negative 10 to the n over n factorial. And we'll find the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Now inputting n plus 1, we'll have negative 10 to the n plus 1 all over n plus 1 factorial multiplied by n factorial over negative 10 to the n. So that's the limit as n goes to infinity of negative 10 to the n times negative 10. N plus 1 factorial is n plus 1 multiplied by n factorial. And now the negative 10s to the n cancel, the n factorials cancel. We can absolute value that negative 10, and we'll have the limit as n goes to infinity of 10 over n plus 1, which is 0, which is less than 1. So by the ratio test, this series is absolutely convergent. Right, once again, something with powers. Not immediately obvious that the root test will work, so let's apply the ratio test again. The root test works best when you have something simply to the nth power. The problem with that denominator is the 4 to the 2n plus first power. So our a sub n is 10 to the n over n plus 1 multiplied by 4 to the 2n plus 1. So we'll find the limit as n goes to infinity of a n plus 1 over a n. So inputting n plus 1, we'll have 10 to the n plus 1 over n plus 2 times 4 to the power of 2 times the quantity n plus 1 plus 1. Multiplied by 4 to the 2n plus 1 and an n plus 1 all over 10 to the n. So now in this exponent, just note that you're going to actually have that the power is 2n plus 3. So this is the limit as n goes to infinity, 10 to the n times 10 multiplied by n plus 1, 4 to the 2n plus 1 over n plus 2. Now 4 to the power of 2n plus 3 You can think about that as 4 to the 2n plus 1 plus 2. So that will be 4 to the 2n plus 1 multiplied by 4 to the second, and then times 10 to the n. That's not the only way to simplify this, but that's one particular way. So the 10 to the n's can cancel, the 4 to the 2n plus 1's can cancel, and we will have the limit as n goes to infinity of 10n plus 10 over 16n plus 32, which will equal 10/16 or 5/8, which is less than 1. So by the ratio test, this series is absolutely convergent. This series is absolutely convergent. Now this next series, you could try to apply the ratio test. Don't think it's going to work, but it looks an awful lot like something over n squared. Also, the -1 to the n means you could probably apply the alternating series test. However, I think it's probably easiest just to use comparison. So what you can note is this. At the absolute value of -1 to the n, arctan of n over n squared, that's less than or equal to pi over 2 over n squared, which is certainly less than something like 3 over n squared. And the reason that this whole pi over 2 jump is true is that arctangent as a graph looks like this, and it has a horizontal asymptote at pi halves and at negative pi over 2. In other words, the range of arctan is negative pi halves to pi halves. And since the sum from n equals 1 to infinity of 3 over n squared is finite, since this is convergent, it's a p-series with p equal to 2. We know that by direct comparison, the sum from n equals 1 to infinity of the absolute value, -1 to the n, arctan n over n squared plus, just n squared, excusez-moi, is also convergent. Remember, the implication there is that if the larger series converges, the smaller one must also converge. So this means, so our original series is not only convergent, it is absolutely convergent. Let's determine whether this series is absolutely convergent, or conditionally convergent or divergent. So here I'm going to use a combination of comparison and the ratio test. So first, start by noting that the absolute value of cosine of n pi over 3 over n factorial, that's less than or equal to 1 over n factorial. And that's because cosine's range is -1 to 1, so the largest that cosine ever is 1. So what we're going to do now is we're going to show that the sum from n equals 1 to infinity 1 over n factorial converges using the ratio test. So let's let a sub n equal 1 over n factorial, so we'll find the limit as n goes to infinity of an plus 1 over an. So that'll be 1 over n plus 1 factorial multiplied by n factorial over 1. So that will be 1 over n plus 1 times n factorial multiplied by n factorial over 1. And the n factorials cancel, giving you a limit that is just equal to 0. So thus the sum from n equals 1 to infinity, 1 over n factorial converges. And by direct comparison, the sum from n equals 1 to infinity of the absolute value cosine n pi over 3 over n factorial also converges. So the original series is absolutely convergent. With this next example, it appears that the negative 1 over n makes it easy to apply the alternating series test. So here we're going to apply the AST. So let's let b sub n equal 1 over ln n. We must show that the limit as n goes to infinity of the b sub n's is 0, so the limit as n goes to infinity of 1 over ln n is indeed 0. And also, it is the case that ln of n plus 1 is bigger than ln of n. So 1 over ln n plus 1 is less than 1 over ln of n, i.e. bn plus 1 is less than bn. So because those two conditions are met by the AST, this series converges. However, if you take the absolute value of this series and get the series n equals 2 to infinity 1 over ln of n, this diverges. You can, pretty sure, use direct comparison to show that. So this series is an example of one which is conditionally convergent. Now here, because we have all the terms raised to the nth power, let's apply the root test. So find the limit as n goes to infinity of the nth root of the absolute value of the terms. So that will be the nth root of n squared plus 1 over 2n squared plus 1 all to the nth power. So that just leaves us with the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1, which when we divide the numerator and denominator by n squared is 1 plus 1 over n squared over 2 plus 1 over n squared, which is a half. And since that's less than 1, by the root test, this series is absolutely convergent. Next, we'll use a test we haven't used in quite a while. So this example, this series looks an awful lot like the harmonic series, sum from n equals 1 to infinity of 1 over n, which we know diverges. But direct comparison will not work, as this is smaller than that. The terms of this are smaller than that series. So we'll use the limit comparison test with 1 over n. So let's let a sub n be the terms of the original series, and b sub n be the terms of the other series. And the limit comparison test says that if this limit is equal to a finite number, then both series do the same thing. So we find the limit as n goes to infinity of an over bn. So that will be 3 over 2n plus 1 multiplied by n over 1, or the limit as n goes to infinity of 3n over 2n plus 1, which is the same thing as the limit as n goes to infinity of 3 over 2 plus 1 over n, 3/2. So as the sum from 1 over n diverges by the limit comparison test, the sum from n equals 1 to infinity of 3 over 2n plus 1 also diverges. Now the next series looks a little strange, but what you should notice is since pi is approximately 3.14, what we actually have here is a geometric series with r equal to pi over 4, and since pi is 3.14, this is actually less than 1, so this is going to converge. And in this case, we can actually figure out what this converges to. Now, remember that we had that the sum from n equals 0 to infinity of a r to the n is a over 1 minus r. Now, the problem with this series is it begins at 1, so we have to change the indexing set. So we start at 0 up to infinity. And now the first term here is pi quarters, so we'll have to make the power on pi quarters n plus 1. And then that can be expressed as the sum from n equals 0 to infinity of pi quarters times pi quarters to the n. And in this case, the a is pi quarters and the r is also pi quarters. So this sum will be pi fourths over 1 minus pi over 4. And I can multiply the numerator by 4, the denominator by 4, and that will simplify to pi over 4 minus pi. So the question didn't actually ask us to find the sum, and it isn't the case that you can with geometric series, but often in many cases you can't find the sum. But since we could, it's good practice. So determine whether this series is absolutely convergent, conditionally convergent, or divergent. So we have the numerator is a product of all the even numbers, and the denominator is a product of every third number. So when we find the limit as n goes to infinity of an plus 1 over an, let's see what happens. So first of all, those negative ones are going to go away, so I'm not going to worry about them. So when I plug in n plus 1, I will have 2 times 4 times 6, and then 2n, and the next term will actually be 2 times n plus 1, or 2n plus 2. And the denominator will have 2 times 5 times 8, up to 3n minus 1, and then 3 with an n plus 1 minus 1. Multiplied by the reciprocal of what we already have. So 2, 5, etc., 3n minus 1 over 2, 4, 6, up to 2n. So quite a bit of things will cancel. So everything up until 2n and 2n, everything up until 3n minus 1. So that gives us the limit as n goes to infinity, 2n plus 2 over 3n plus 2, which you've seen enough of those to know that that limit is actually 2/3, which is less than 1. So by the ratio test, this series is absolutely convergent. the terms of a series are defined recursively by the equations below. Determine whether the sum of the a sub n's converge or diverge. So here we'll find the limit. We'll use the ratio test. A n plus 1 over a n. So because we have this recursive definition, the n plus first term is actually 5n plus 1 over 4n plus 2 multiplied by an, and we divide that by an, and the a sub n's cancel out. We have the limit as n goes to infinity of 5n plus 1 over 4n plus 2. You can see tons of these limits now, so you know that this limit is equal to 5/4, which is greater than 1. So, in this case, that tells us that the sum from n equals 1 to infinity of these a sub n's diverges by the ratio test. And here's another one of those examples. So we'll find, once again, we're going to try the ratio test. So an plus 1 over an. So the limit as n goes to infinity of 2 plus cosine of n over root n multiplied by a sub n and then divided by a sub n. So that's the limit as n goes to infinity of the absolute value of 2 plus cosine of n over root n. And you can actually prove that this limit is equal to 0, which is less than 1. And here is how you prove it using the squeeze theorem. So cosine is in between -1 and 1. So 2 plus cosine n over root n. If cosine is equal to 1, the greatest this could be is 3 over root n. And if cosine was negative, the lowest this numerator could be is 1, so 1 over root n. And the limit as n goes to infinity of 1 over root n is 0, and the limit as n goes to infinity of 3 over root n is also 0. Thus, that limit is also 0. So, as the limit of the n plus first over the nth term is 0, which is less than 1, by the ratio test, the sum from n equals 1 to infinity of the a sub n's converge absolutely. The final thing we're going to go over in this section is we're going to find the values of x for which certain types of series converge. So here we have the sum from n equals 0 to infinity of 2 times x over 3 to the nth power. Now we did something like this in a previous section. This is a lot like a geometric series. So it's a geometric series with r equal to x over 3. And you know that this will converge if the absolute value of x over 3 is less than 1, which implies that -3 is less than x, which is less than 3. So it converges for x is within that interval. Officially, we're also going to test -3 and +3 to test at the endpoints. With geometric series, those are never going to work, but in the next case, we'll have one endpoint work and one not. So if you tested -3, this becomes the sum from n equals 0 to infinity of 2 times -1 to the n. And this diverges, by the test for divergence, because the terms oscillate between +2 and -2. And if you test +3, we have the sum from n equals 0 to infinity 2 times 1 to the n, which also diverges. So this series diverges if you have x values between -3 and +3. In the next example, we will figure out which values of x for which this series converges using the ratio test, because this is no longer a geometric series. So we'll find the limit as n goes to infinity of the ratio of the n plus first to the nth term. So the n plus first term is x plus 3 to the power of n plus 1 divided by n plus 1, and then multiplied by n over x plus 3 to the n. Now, x plus 3 to the n plus first is the same thing as x plus 3 to the n multiplied by x plus 3, and then times n over n plus 1 and x plus 3 to the n. Now the x plus 3 to the n's cancel, and we have the limit as n goes to infinity, absolute value x plus 3 times n over n plus 1. And x plus 3 absolute value is just some kind of constant. This limit as n goes to infinity of n over n plus 1 will be 1. So the limit of this expression is just the absolute value of x plus 3. And we know by the ratio test that this series will converge if the absolute value of x plus 3 is less than 1. When the absolute value of x plus 3 equals 1, the series may converge or may diverge, and we will have to check those cases individually. But x plus 3 quantity absolute value being less than 1 implies that x plus 3 is in between negative 1 and 1, or that implies that negative 4 is less than x, which is less than negative 2. So as long as x is within between negative 4 and 2, we know that this series will converge. Next, let's test the individual endpoints, negative 4 and negative 2. So if x is equal to negative 4, your series becomes a sum from n equals 1 to infinity, negative 1 to the n over n, which you know converges by the AST. We proved that in a previous lesson, so I'm not going to go through the details again. If x is equal to negative 2, your series becomes the sum from n equals 1 to infinity, 1 over n, which you know diverges because it is the harmonic series. We proved divergence earlier. So your final conclusion is that your series converges if x is bigger than or equal to negative 4 but less than negative 2. Or you could say x is in the interval including negative 4 but not including negative 2. Those are equivalent. This little symbol means in. You can also just write out the word in and they'll be just fine. We'll be doing a lot more of this type of stuff in a later section.